will be the last time you guys did that. He wrote 400 and they asked him to write.
Yeah.
I did it to where like if I had one more paragraph, it'd be 1100.
Okay.
Why would I write? Like repeating. Well, 400 is not even half.
Okay, suppose I have variant factors of a matrix. Notice in this example, I haven't specified the field, and you also may say, given Sophia's pointed question at the end of last time, hey, there, Houdini, where did these come from? And I'll address that in a moment. But let's just suppose that from on high, I am given that I've got a matrix that has these invariant factors. Let me kind of multiply these out because I might need that for some of this. X4 plus X squared. And this is X7, right? Plus 2X5 plus X cubed. Okay, query. What's the dimension of my vector space that this one transformation is acting on me?
13.
13, that's right. It should be, and in fact, the characteristic polynomial should be x times x4 plus x squared times x7 plus 2x5 plus x cubed. Whatever it is that you get when you multiply this all together. By the way, is this matrix singular or non-singular? It's singular, right? Because one of the eigenvalues is 0. However, it will not be nilpotent because not all the eigenvalues, assuming that you could extract this polynomial, are 0. Okay, so let's look at this first. Let's look at the rational canonical form. This is going to be everybody's favorite 13 by 13 matrix. I'm going to go by the invariant factors. The first thing I get is a 1 block, which is just 0. I get another 1 block, which is 0. And of course, 0 corresponds to the constant term coefficient here. Now I get a 4 block. Don't I? Yes, block. And I get 0, 0, minus 1, 0. That corresponds to the quartic invariant factor. And how about the 7th one? Yeah, we get a 7 block. 0, 1, 0, 0, 0, 0. One more 0. 0, 0, 1, 0, 0, 0, 0. 0, 0, 1. 0, 0, 0, 0, 1, 0, 0. 0, 0, 0, 1, 0. 0, 0, 0, 0, 0, 1. And finally, I guess I get linear, constant linear, quadratic, cubic, 4th degree, 5th degree, 6th degree. There we go. The rational canonical forms will be that. Everybody okay with it? Now, at this point, I can't go on without more information. Does somebody tell me why? Anybody know why I can't go on without? There's not enough, I don't have enough information just from what I've given you so far to proceed to the primary or the Jordan. To get the primary rational canonical form, I need to know prime powers, right? So let's see what happens. Let's try to get elementary divisors here. Well, okay, for sure X is one of them. Because X is certainly a prime, and so is X, and X squared, and X squared. So there. These, oh, I'm sorry, middle was executed. My bad. Those are the prime powers that appear in the invariant factors, right? But now, what do I have to do to proceed forward with X squared plus 1? It is either irreducible, synonymous with prime if you're over a field, or and actually that makes a difference too, doesn't it? There's actually two cases. Or that's a possibility as well. You can have multiple of this, right? Yes,
If you were working over, like infinite polynomials as well, or that we know that can't be true because we're working with matrices, so everything's finite dimensional.
what you're thinking.
Like, uh, in algebra 1, when you had the double brackets around the x, like you had R double bracket x.
Mhm.
That,
That's power series.
yes, the power series, yes.
Okay, so
So, in the power series, x squared plus 1 was have a inverse, no?
yeah, but we're not concerned with power series here. This is all polynomials. But there's three cases here. So so the rational canonical form, that's set in stone. Everybody okay with that? So let's go through the cases for the primary and Jordan form. Oh, I probably shouldn't have done that. I'm gonna record these over here before I forget them. X squared times x squared plus 1, x cubed times x squared, which is okay. So let's go through the primary and the Jordan with case 1. X squared plus 1 is irreducible. Then the primary, then invariant elementary divisors are x, x, x squared, x cubed, x squared plus one squared, and x squared plus one and x squared plus one squared. It's 4. So the primary rational canonical form is this. 0, 0. Now this corresponds to a 2 block. And this corresponds to a 3 block. And 0, 0, 0. So that takes care of this. Now I've got a 2 block here. And now I've got a 4 block. And -1, 0, -2. 4, 5, 6, 7, 8, 9, 10, 12. Wait a minute. Okay, good.
Why is there not, like in the 2 and 3 block, why is there not a -1?
In the 2 and 3 block. You mean right here?
Mhm.
Because remember what this is this is 0 plus 0x plus x squared. And the other one is 0 plus 0x squared, x plus 0x squared plus x cubed. And remember, these are the coefficients that show up in the 2 block and in the 3 block. Right, it's the ones of lower degree than the highest.
Oh wait, for the like x squared plus, oh, never mind. It was the next one. Okay.
Okay, everybody understand how we got this? Jordan canonical form. None. Because you can't, if x squared plus 1 is irreducible, you can't get it down into the power. For the Jordan form, you need to be able to get every one of the prime powers down into a linear polynomial to a power. And you're stuck here. 2. What happens if x squared plus 1 is x plus alpha, x plus beta, with alpha not equal to beta? Well, in this case, this means these are 2 separate primes, right? And so my elementary divisors are x, x, x squared, and x cubed as before. And then I have x plus alpha, x plus beta. The 2 factors from, this is what I get when I factor this down, and x plus alpha squared, which is x squared plus 2 alpha, x plus alpha squared, and x plus beta squared, which is x squared plus 2 beta x plus beta squared. Everybody see how I got those? And of course, in the familiar thing, what you're used to is alpha being I and beta being minus I. For example, this is complex numbers. So what happens here is we tend to have smaller blocks. That's 1 block, 1 block, 2 block, a 3 block, another 1 block, another 1 block, a 2 block, minus alpha squared minus 2 alpha, and another 2 block, 0, 1 minus beta squared, 2 beta. Should be about 2, 4, 6, 9, 11, 12. Good. Everybody okay with that? And the Jordan form is slightly different. it's almost like this. Most of the blocks are the same. 0, 0. This actually takes on the Jordan. This is because the eigenvalue here for x squared is 0. And same for this 3 block with x cubed. These blocks are the same. Because the eigenvalues. These are a little different. These two that came out of the primary, they are minus alpha, 0, 1 minus alpha, and minus beta, 1, 0 minus beta. So notice that there's just a little slight kind of perturbation of the last two blocks, but again, the Jordan forms upper triangular, right? Everybody see that? Last case is when there's kind of a specific class that this applies to. Anybody know where this is significant? Anybody know the characteristic of fields that make this happen?
Is it bottom characteristic?
Characteristic 2. This will happen in characteristic 2 because what happens when you square this in characteristic 2, you get x squared plus 2x plus 1. But the 2x is now 0. Right? Everybody agree with that? So this happens if you have a field with characteristic 2. Then the elementary divisors are x squared, x cubed. Right. X plus 1 squared and x plus 1. Well, let me write this out. And x plus 1 to the 4th, x plus 1 squared, which is actually x to the 4th. Right, so all the intermediate terms are, which is actually that. Anybody okay with that? So let's see what this looks like. So the primary rational canonical form . Okay, there's your x, x squared. Yeah, these are all kind of the same here. Now let's go on to these other ones. Again, we've got this block here. It's like 0, 1, 1, 0. Why did I write 1 instead of -1? That's right, they're the same because we're in characteristic 2. I mean, I could write -1 here. Maybe that'll avoid some confusion, but -1 and 1 are the same in this characteristic. And for the last one, I get a 4 block, I guess, which is 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 1, and -1, which again can be 1, like that. So there's your primary rational canonical form. Yep. And Jordan canonical form. Uh, 0, 0, 0, 1, 0, 0, 0, 1. And now I have to pick apart this. This has eigenvalue -1, which is the same thing as 1. and it's a 2 block. And finally, we get a 4 block here. And again, in this one, all the minus ones could also be 1. Okay, everybody see how to do that? How to given the invariant. So do you feel like if I walked up to you on the street, gave you some invariant factors, you could kind of sort this out? Well, and of course, now the $64,000 question is where do you get invariant factors? So let me give you a theorem that I won't prove, but I will actually go through the pains of deriving one. Conveniently, one of them from your homework, I'll do it by hand. Yes, go ahead.
Why couldn't we get the Jordan for the first one with, for the first case when it's irreducible?
Because in this case, the Jordan, all the invariant factors, like this one was like x squared plus 1, which is a linear squared. And this is x4 plus 1, which is a linear to the 4th power. But with in the case of, so we got the primary and the Jordan here. And you can always get the primary, but the question, so which one was the previous one?
It was
The
where,
first-
sorry, it was where x squared plus 1 is prime.
Right, so if what we had, so the situation where we couldn't find the Jordan form was x squared plus 1 is irreducible. Which means you can't write this as a power of a linear polynomial. Right, this is not equal to x plus something squared.
Okay,
And that's what you need for the Jordan form is you need to be able to write every irreducible. You need to be able to factor every polynomial. Let me restate this carefully. If we want every matrix over field to have a Jordan form, that means every polynomial of that form has to factor down into linear polynomials, right? And that's not even true over the real numbers, right? Now, just because you have a matrix over Q doesn't mean it doesn't have a Jordan form. It depends on how the polynomials and the invariant factors factor. For example, if all the polynomials are powers of x and x plus 1, then you're good to go. It'll have a Jordan form. If that's not the case, right? Like if you get something with complex conjugates, or if you're over the rationals, you get something like x squared minus 2, and radical 2 is not a rational number, you would have to go to a larger field and consider it over a larger field if you want to get the Jordan form.
okay,
And actually, we'll always be able to do that because we're fixing to come up on field theory, and if you have a polynomial and it doesn't factor into linear, so it didn't have all its roots in the field, you can just make it bigger and make it so the polynomial does factor, which is really kind of groovy. So let me give you a theorem here. So suppose, and this is key to answer the invariant factor thing. Let A be an n by n matrix over a field. So this is here 1327. Let A be an n by n matrix over some field F. Then the matrix of polynomials, then the matrix okay. By the way, this should be a familiar thing. This is basically the setup that you use to find the eigenvalues, right? You subtract it. Actually, I've got it in the other order, but I mean, you know, yours was maybe a minus x, in. You subtract x from the diagonals and you just kind of go for it. This is equivalent via elementary row and column operations over kx. I don't mean equivalent via conjugation, so let me make this clear. Via elementary row and column operations. Over kx. Now, I'm not allowed to invert any polynomial of positive degree, right? So you remember when you do row and column operations, you can divide out stuff. You can divide out by everything that you can divide out by something here only if it's a unit in kx. You can't divide by x, for example. So that's what I mean by over this ring kx. To a diagonal matrix with entries f. This is f. To a diagonal matrix with diagonal entries f1 divides f2 divides fk. Or no, I'm gonna go all the way up to n because I'm gonna let some of these be ones. The non-constant fi's are the invariant factors. This little piece of magic will do it. So here's what you do. You want to know the invariant factors of your matrix A, subtract x from everything on the diagonal, and just row reduce it until you get a diagonal matrix. Once you achieve that diagonal matrix, the columns, the diagonal entries, you should be able to arrange it so the diagonal entries divide each other successfully. Some of them may be constants or ones. All the ones that are of degree 1 or higher are the invariant factors of A, which is kind of cool. This really depends on the fact that fx is a Euclidean domain. Yes.
Sorry, is there a closing parentheses after the fx? Let me give an example, and I'm sure you will appreciate this example. You should be able to do this. Actually, I did this by myself hand for both of your homeworks the other day because I got so annoyed with Wolf from Alpha because nothing seemed to be working right. Although I do believe, does anybody know if we still have a subscription to Maple? I think we do. Yeah. Maple will do this nicely. What this reduction is the matrix. When I get it into this diagonal form, it's called the Smith normal form. So that's the buzzword you're looking for. And by the way, I don't care if you do that to figure out the invariant factors on the matrix. Just tell me what you did, right? I don't expect you to do what I'm fixing to do here. Let's let A be -1, 2, -1. And listen, I really want you guys to watch me on this because I'm going to do this without the paper. And if I get this wrong, believe me, we're all going to regret it. 1 and -1, 1, 0, 1. I believe this is actually one of the matrices from your homework. So let's find the invariant factors. This is called Smith. So. Okay. I hope you all will forgive me because I'm going to be rather liberal with my computations. I want to kind of, because really, all I have to do is row operations. So the first thing I'm gonna do is I'm gonna put, just so we know. So show up. Okay, so the first thing I'm gonna do is I am going to key on this row to wipe everything out, right? And I'm gonna put it on top, right? So see, I'm going bananas with this. Let's see, 1 minus 1, 2 minus x, 0. So I've just basically moved this to the top. I'm gonna shuffle things as I would, yes.
So the minus x, like, we can do it, it will give us the same invariant factors, if, or will it negate the net?
Oh, yeah, it doesn't matter because, at most what you'll do is change the sign of the polynomial and that's still gonna be the invariant factors, yeah. So, let's see. I guess what I'm gonna do is the second thing, I'm gonna add these two rows, I'm gonna put it in the second one, so that's gonna be 0, 0, 2 minus x. Boy, I've been lucky so far, 1 minus x. Everybody agree with that? I guess I'm gonna multiply this by 2 and kill this thing, so that's gonna be a 0. Let's see, times 2 and add, that's gonna be 1 minus x. Times 2 and add, so that's gonna be 3 minus 2x. Yeah, and 0. Everybody agree with that one? And the last thing I'm gonna do is I'm gonna multiply this by, I guess, minus 1 minus x and add.
Dr. Courtney,
Mhm.
are you not using the third row instead?
Oh, thank you. That's a better idea. 1 minus x and add, yeah, thank you, because I almost bit it there. So multiply that by 1 plus x and add,
Yeah.
right?
Yeah.
So multiply this by 1 plus x and add, so I'm gonna get a 0. That's gonna be 1 minus x. Everybody agree with that? Times 1 plus x and add, so it's gonna be 1 minus x. Times 1 plus x, that's going to be an add. So it's gonna be something like, minus x squared. Plus x, so that's gonna be x. And it's going to be 2 minus 1. That look right to you guys? Minus x squared. 2x minus x is x, add that up. And then 2 minus 1 is 1. That looks right. Everybody okay with that? And then and that's gonna be 0.
And that one we can use like this,
What's it now?
that one we can use roll for alpha. Or like, what do we
Yes.
use roll? Oh, okay.
Yeah. If you know how to input the stuff better than I do, maybe Maple will be better, but it just kept giving me the stuff I wasn't asking for. And now watch this. I'm gonna use this column to just wipe all this crap out, right? I don't even have to do anything, because these are all zeros. Just kill, kill, kill. It's a murder spree, and nothing happens down here, right? So this is equivalent to a much easier matrix: 1, 0, 0, 0, 0, 0, 2 minus x, 1 minus x, 1 minus x, 3 minus 2x, 0, 1 minus x squared plus x plus 1, 0. And I guess So now I'm gonna suppress this down to a 3 by 3, so I don't have to write as much every time, right? Because I've already got one of my diagonal entries. One of my diagonal entries is 1. Everybody agree with that? And so now I'm just gonna muck around with the smaller 3 by 3. Everybody cool with that? I'm gonna put you on top. Right, so I'm gonna do the 3 by 3. I'm gonna put 1 minus x, 3 minus 2x, 0 on top. Then at the next level, I'm gonna put 0, 2 minus x, 0, or I'm sorry, 1 minus x. So that was just a copy job. And here, I'm gonna multiply by -1 and add here, so that's gonna be a 0. Times -1 and add, so that's going to be minus x squared minus 3x. I'm sorry, plus 3x. That's going to be minus 2. Everybody okay with that? Now, it's not as convenient as before, is it, right? Because last time I had that one that take everything out. But what I am going to do is I am going to, I'm gonna kind of reduce this column here a bit. So I'm gonna multiply this column. I'm gonna multiply this column by -2 and add it here. So that's going to be, the 2 x's cancel, and I'm gonna get 1 here, and everything else is the same. Everybody okay with that?
You what?
I multiplied this column by -2 and added it to this one.
Ah, yeah.
And that gets that down to a 1, nothing else has changed. Everybody okay so far? Okay, any ideas for the next move? I tell you what, I'm gonna use this one to take out these. It's gonna create more stuff here, but I think I can deal. 1 minus x, 1, 0. First I'm gonna multiply this by x minus 2 and add it here. So that's going to be, what did I say, by x minus 2? So that's going to be 1 minus x times x minus 2. That's going to be 0, and that's going to be 1 minus x. And I'm going to multiply this by this thing. And by the way, this thing here, I might start writing it this way. This is minus x minus 2, x minus 1. Notice there's lots of common factors here, right? Do I agree with that? So here, I'm going to multiply this by, well, so let's see what I get down here. This is going to be, again, 1 minus x, x minus 2, same as before. This one is going to be x minus 2. So what goes here is x minus 2 plus, well, negative x minus 2, x minus 1. Agree? Right, when I multiply this by x minus 2 and add it to this, I should get x minus 2 plus this, right? And this turns out to be x minus 2 times 1 minus x
plus one. So it's minus x minus two squared. Everybody okay with that? And this, fortunately for us, is just. Okay, anybody see what we can do now? I can use this column to take out the middle term in this. Everybody agree with that? All I gotta do is multiply this by two minus x and add it. And then I've got zeros here, so it doesn't change anything. Everybody agree with that? So would you all forgive me if I just did this? That's a zero. Right? So now at this point, I have the matrix. I'll write down here, let me write it down here for hopeful clarity. Zero, zero, one minus x. One minus x, x minus two, minus x minus two squared, zero. So I've got it a little bit easier, right? And now, I guess, let's see, that's gonna kill that. And, oh, I guess I'm going to do here. Now, what I've got here, it looks like I've got one invariant factor of, I can rearrange this matrix by swapping this row and this column. So this is 0, 0, 1 minus x. 1 minus x, 1, 0, and 1 minus x, x minus 2, minus x minus 2 squared, 0. And now I can swap these two columns. And I get 1 minus x. 0, 1, 1 minus x. And finally, 0. And 1 minus x, x minus 2. Everybody okay so far? Yep. So now I'm going to work on this one right here. It looks to me like I've got an invariant factor here, 1 minus x. I'm going to work on the smaller 2 by 2 that I've got in that lower right corner. And now I have 1 minus x minus 2 squared. 1 minus x, x minus 2. Now, I guess what I want to do is yeah, I guess it doesn't matter that much. I'm going to take this column out. I'll multiply this by x minus 1 and add it here. Multiply by x minus 1 and add. Multiply by x minus 1 and add. And so I get 1 minus x, x minus 2, minus x plus 1, x minus 2 squared. And I bet this simplifies nicely. Sure I did that. Comes x minus 1 and add. Times x minus one. X minus one. Okay, so it looks to me like I can pull out, let's see, one minus x, x minus two. Let's pray we've got the signs right. This is one minus x, x minus two. This leaves a one. This leaves a change of sign. So does that look right to you guys?
Yeah.
Yeah, that's right. So this is minus x minus one squared, x minus two. Because that sucker's an x minus one. So this is 1, 0 squared. And this is minus x minus one squared, x minus two. Everybody agree? And now I just use this row to take this out. 1, 0, 0 minus x minus one squared, x minus two. And so it looks to me like what we get, if we put this all back together, is our diagonal matrix after we've reduced it to be 1, 0, 0, 0, 0, 1, 0, 0. I got that one x minus one invariant factor. And this last one. And let's see, that's degree 3, 4, good. So it looks to me like for this particular matrix that we started with, the invariant factors are x minus one quantity squared times x minus two. But you know what? That's your homework problem. Just get, if I were you, I would check me with some online thing to make sure. I'd have to be pretty lucky, unlucky to actually get something that makes sense like this, you know, because usually if you make a mistake, you get things that don't match and whatever. But anyway, so this is not something that you would usually do by hand, although I tell you, I did the 5x5 one on my homework too, and I remember thinking that was a little bit easier. But that kind of brings this to a wrap. Any questions? Yes.
Oh, I was gonna ask, are we gonna have to do this on the exam?
What? This?
Yeah.
Okay. Let's think for a minute. Who grades the exams?
You.
Do you think I'll be able to read it? You should have that power, Gandalf, but you know, I don't want you to overdo some stuff.
Okay.
It only took like basically all of that.
Right, and that's the problem too, because what do I learn about what you know? Because any human being in there could make the silliest mistake, and then it's all just a dumpster fire,
Right.
and then, you know, you got nothing.
So the invariant factors is x minus one and negative x minus
Yeah,
one?
you're right, the invariant factors, and a good gut check is, when you arrange it in increasing order, you should have division, and it's okay here, this divides this. But yes, the non-constant polynomials that show up here should be, there's two things that should happen, they should be the invariant factors, and when you multiply them all together, you should get the characteristic polynomial. And the largest invariant factor is in fact the minimal polynomial. So whatever this linear transformation is, its characteristic polynomial is x minus one cubed times x minus two. That's its minimal polynomial. Right. So.
As in like the minimal one that annihilates.
That's correct. That's right. Okay. I think we have just one. So we're going to start the coolest thing ever. Fields and Galois theory. This is just really some pretty stuff. We're going to talk about fields first, the general structure, and then we're going to get to the Galois theory. That's a nice meeting of groups and fields.
So let me leave you with the following definition, which is kind of an interesting way to think about it. Definition. A field K is a commutative ring with identity. Anybody think of a way to characterize fields in terms of their ideals?
Where 0 is the next one?
Good. So somebody likes an ideal theorist might think of fields as very boring because 0 is maximal ideal, it's the only proper ideal. But it gives a rich structure because fields are where the units are important. Everything's a unit. So we will pick up there next time. Any questions? Yes. All right, you all have a good one.